Our topics in this section are all building up to our ability to be able to sketch the graphs of rational functions. Before we do that, though, we want to revisit a topic from earlier in the semester, which was the library of functions. We've talked about specific types of graphs so that we have a picture associated with that word or that equation so we know what sort of our starting picture looks like as adjustments begin to get made. In this case, what we have graphed below is the reciprocal function, y equals 1 over x. So we're graphing that very simple rational function. Two things to identify right off the bat from the picture here is that this graph has what's referred to as a vertical asymptote, which is essentially an invisible boundary that our graph will never cross over. So this vertical asymptote is defined in this case by the equation x equals 0. So we draw that as a dashed line to indicate that it's not a line that actually exists as part of our curve, but as our function approaches x equals 0, it will get closer and closer without ever actually crossing over that line. We also have what's referred to, in this case, as a horizontal asymptote. In this case, defined specifically by the line y equals 0, that horizontal line. Horizontal asymptotes deal with the end behavior of our function and reference the idea that as our values for x grow increasingly large towards positive infinity or increasingly small towards negative infinity, what we have is some line or some value that our function is approaching closer and closer to. So the first thing we have to note there are the inclusion of these asymptotes. We can also talk about the domain and range of our function. In this case, for our domain, that vertical asymptote represents a value that our function will never cross over. So we have to remove x from our domain, and we can do that in interval notation by saying the interval from negative infinity to 0, union 0 to infinity. Using the rounded parentheses gives us an open end at each of those intervals so that all numbers besides 0 are included. For the range, similarly, we'll never hit a y value of 0, so we need to remove y from our range. And we'll do that using similar interval notation, eliminating that value of 0. We can also talk about where our function is increasing and decreasing. In this case, as we follow our graph from left to right, that curve is always following a decreasing pattern. So we would say that our function is never increasing. And then we could say that it's decreasing on the interval from negative infinity to 0, union 0 to infinity, where again we're leaving out that value of x equal to 0 since our function's not defined there. We can also identify this function as an odd function since it's a reflection of itself across the x-axis and then across the y-axis. In example 1, what we have is a translated and adjusted rational function, 1 over x. We want to look at this graph and use it to find the domain, range, intercepts, and equations for all asymptotes. We can start off by indicating our asymptotes. In this case, our x-asymptote, or our vertical asymptote, has been shifted over to the left by 2 units and is now defined by the line x is equal to -2. Our horizontal asymptote has been shifted up 1 unit and is represented by the line y equals 1. So our domain in this case will be all real numbers except for -2. So we'll use a similar notation that we used above, except in this case it will be that value at -2 where we have that break between the two intervals. And for our range, we'll have our break at +1. This function has two intercepts. We have a y-intercept occurring at 0, 1.5, and we have an x-intercept occurring at -3, 0. So with this updated translated function, what we have are our horizontal and vertical asymptotes identified in equation form. We've identified any intercepts if they exist, and we have updated statements for the domain and range with, again, those breaks represented at those points where we have undefined values for x or y.